So good afternoon, everyone. Good afternoon, everyone. This is Dr. Sohail Pervez. I welcome you for this last session from my side on the materials. That is the phase diagram, then heat treatment stress strain diagram for engineering materials. In the last lecture, that is lecture number 5 of continuation of our lecture series, we have introduced ourselves with the phase diagrams. Now, when we say phase diagrams, these are nothing but the representation of basic properties of material in terms of its microstructure, wherein the diagram is a graphical representation. The phase diagram is generally represented in terms of temperature, composition, and pressure. So pressure again is a very important aspect. Now, as far as pressure is concerned, I'm continuing with the last lecture. So phase diagrams are nothing but representing the basic idea of a material in terms of its properties. So the next. Now, why do we draw equilibrium or phase diagrams? It shows various phase present at different compositions and temperature. Now, this is the most important part in getting the characteristics of a metal as well as non-metal as to how its composition will be affected by the temperature, change in temperature or rise in temperature. Now, since we have different materials, unary, binary, tertiary also, so it shows basically the phases present in the material. It indicates solid solubility of one element into another, which is very much important for our alloying. That is again a very important part, alloying part. So again the same thing. Yeah. The next element is it shows a temperature range. It shows temperature range. Now, when we say temperature range, it means that the amount of temperature required to solidify or liquidify a material when it is heated or cooled down under secured or controlled condition. The next, it indicates temperature at which different phases starts to melt or different phase starts to melt. Now, there are a few terminologies which we'll be using throughout our lecture. That is system. Now, a system may be the composition of solid, liquid, gases, or the combination of any of the metal. But the system will be unaffected by its surrounding. That is very important. The next is phase. It is basically the physical composition, chemical also, substance separated from the other portion of surface and interface. So each phase will represent its own identity. Let it be solid, let it be liquid, it will represent, and that is known as phase. Next is variable. Now, when I say variable phase, obviously variable of the phases, how many variables will be required to define that particular phase? So a particular phase exists under various conditions of pressure and temperature and composition. Now, when we say composition, it means that the system will be affected by all these three parameters. Next, components. Now, when we say components, so the components will be again the same thing. chemical compounds or the substances present in the system, allowing it's a mixture of two or more element having metallic properties. So that mixture is generally known as alloy, as we all know. Now, to control any phase diagram or phase change or phase representation diagrams, the most important rule is known as Gibbs rule, which we have studied in the last lecture also, and it is represented by the mathematical representation P plus F is equals to C plus 2, where P is number of phases, C the components in that system, F degrees of freedom. It means number of variables that can be changed independently. This is again very much required. So independently, how much we can control. The next is, how do we classify different types of phase diagrams? So single component system, that is called unary diagram. Two component system, binary diagram. Three component system, ternary or tertiary diagrams, wherein the most important part is the number of components in the system. For single component, it means single seawater. Seawater, we'll take the example. Two component system, say iron carbon, PBSN, AgCu. So it all depends. So the next one. Now single component system, we have taken the example of water. We may take diamond also, graphite also, metallic carbon also. If a system consists of just one component, example water, so equilibrium of phase exists, is now represented or depicted by this diagram. Now, how many stages a water can have? How many phases a water can have? So the graph is between temperature and pressure. Since it is a unary, so we are not very much inclined for composition, percentage composition. The moment we'll take a binary diagrams or binary components, then in that case, percentage composition of the materials will come into picture. Now, as we can see at this triple point, we are having three different stages. This equilibrium point, three different stages. So below this triple point, we are having ice. On the rightward, it is water. And above this means if you go on increasing the temperature, the vapor stage will be acquired by the graph or by the system. So this is the phase diagram of single component system. Next, that is two component system. Now this is what we are supposed to concentrate today, and we are about to solve a number of problems over this issue because it is generally asked in the examination. Now when we see two component system or binary system, these diagram constitute two components, two metals, Cu and I, or metal or a metal and a compound, say Fe, iron oxide. So here are two compounds, aluminium and silicon, all the oxides. So thus binary diagrams are usually drawn showing variations in temperature and composition only. Now when we say binary, the component is completely soluble. See, one classification is the components are completely soluble in other component in both that is solid and liquid state. The other part is there are components which are soluble in liquid but are not or partially soluble in solid. So if both the components are completely soluble in each other, the system is called as amorphous system, isomorphous system, and if not, then it is called non-isomorphous system. So this isomorphism is very much of our interest because we are or will be say going to in depth of this particular isomorphous system. So this is the phase diagram representing the isomorphous system, wherein this diagram typically shows temperature and percentage composition of two different metals. Now let us take the example of CuNi. But prior to that, because as we'll be dealing with the numericals itself, so just take this example. We are having two metals A and B. Now these are the percentage of B, percentage of metal B with respect to A. So if I say 10, if I say 10 or 10%, it means that 10% of B in terms of A, in terms of A. So this is again very much required. This is again very much required. Now, from the figure itself, there are few points. There are few points and there are few regions. First, we will talk about the regions. The line A dash, the line A dash B dash, or the curve A dash B dash, and the curve A dash B dash above this particular region separates two basic phases, that is liquid phase of the components and the solid phase of the components, wherein this particular region shows both the liquid as well as solid. That's why this is the mixture of liquid and solidus stage, as it is depicted in the diagram. So this is the liquid. So when we say liquid state, it means the curve A dash B dash. When I say solid, it means A dash D B dash. Now when we say liquid plus solid, again the same, but the representation will be different. Now let us assume that we want to calculate the mass fraction of this particular composition at some distance x from the reference line x. So this would be the distance, say x is there. So we'll draw a perpendicular line on this curve. And let us say at some point C, please try to understand this fact or this particular element. At some point C, we want to know the status of this particular component. So in that case, this line A dash B dash, which is also known as a liquidus curve or curve of liquidus line, and the second one A dash D B dash, known as solidus line or solidus curve. It means that from here to here, the liquid is gently or gradually be shifting into solid state, and liquidus line shows that the leftover solid portion, micro components which are solid right up till now, after the increase of temperature will now transform into liquid state. That is nothing but liquidus line A dash B dash. So this is all about the diagram and the representation. Now, if I wanted to know what would be the percentage of element at this point C, which is at a distance of x composition. Now see, in our discussion, as I have previously told you about the unary system, that in this case the graph would be drawn or has been drawn between temperature and pressure, because here no percentage composition was of importance as far as system was unary. Now the system is binary. So again we have to draw, basically we have to draw a phase diagram taking into account all the three parameters, that is temperature, pressure and composition. Yes, all the three components should have been taken into consideration. But for the sake of simplicity, we have considered pressure at 1 atmosphere, and then the curve has been simplified into temperature and percentage composition of the elements. So this vertical line will represent different phases of the material, as A represent liquidous phase, L. B, this is at this curve or the point at which liquidous line is passing. C, having both the phases, liquid plus solid phase. D, that is solidus line, closer to solid surface or solid constituent. E, completely solid structure. But what would be the percentage at point C, because that is our requirement. So we have to draw a horizontal line passing through the point C and cutting the curve at different points, say U and V. This line is known as a tie line. Now this tie line is used to represent the percentage composition of the elements, under study. Now when we say we'll be using the formulae for this using the lever rule. So in that case, mass fraction, say U dash, it will be represented by CL in the next say PPDs. So U dash and V dash. V dash is nothing but mass fraction of B in solid phase. U dash is in liquid phase, and CO, say at this X. This is CO. Mass fraction of B in A. Because A will be there, but we want to study the composition of B in A. We want to add. Yes, we want to see the phases. So we'll apply the lever rule here. Now, as I have told you, this tie line will cut both liquidus as well as solidus line. So below this is solid, above this is liquid. So we want to calculate the percentage composition in both the phases, because after this point it will be liquid, after this point this will be solid. So we have represented this in terms of mass fraction. So this is the basic formula wherein we are using tie line and we are using it as a lever diagram. That's why it is a lever rule, wherein a fulcrum is there, and this is the mass of solid, and this is the mass fraction in liquid. So the point at which solidus line is cut is generally represented by C alpha, that is solid component percentage composition, and CL, liquidus percentage composition. So the formula would be for liquid, we'll try to remember this as if WL or ML, sometimes it may be ML, somewhere it is in some books it is referred to as ML, somewhere it is WL. So in that case, that mass fraction will be represented by the equation C alpha minus CO upon C alpha minus CL. Now if it had been for solid alpha, then in that case the reference would be CO. The reference will start with CO. So CO minus CL upon C alpha minus CL. So for liquid we'll be using C alpha in both the cases, in both the numerator and denominator at first sight, and for solid we'll be using CL, the percentage or the proportion of constituent in liquid. So these are the two basic formulas which we'll be using while solving the numerical, and I'll be always say giving its reference as a lever according to lever rule. Now we will consider, as I have told you, we'll consider the binary system phase diagram for Mr. Cu and Ni. So copper. So here we have to see the phase diagram representing CuNi system, wherein this diagram, these points A, B, C, D, E will give us the reference percentage by weight of both the Ni and C in liquidus as well as solidus, as well as liquid plus solid phase. So you have to remember, say in liquid, fully liquid phase, percentage of nickel is 35% by weight, and at this point A, Cu will be at yes, Cu will be at 65. Now we come to point B, then in that case we'll have to do is say 35%. Obviously this percent would be same for your Ni. Now alpha will go on changing, say 46% by weight. 46% by weight. Next, at point C, now the liquidus phase is, since this is binary, both liquid and solid phases will be there. So at this case, sir, the liquidus phase would be 32% and this is 43%. Again, this on the solidus line, that is point D, 36% by weight of Ni in solidus phase, whereas 24% by weight on liquidus line. And the last one, point E, this is the solid phase. So this particular diagram or this particular temperature composition curve will be helpful in solving number of numericals. Now there are certain rules, because we'll be always asked with the 3 requirements in any numerical of phase diagrams. So we'll go one by one and see. Rule number 1, if we know, obviously all the way we'll know temperature and composition, that is CO, then we know dash. The first question is which phases are present. Now see, since the system is binary, both the metals are soluble in liquid as well as solidus phase. So in this case, all the 3 phases are present. Which 3 phases are there? Liquid plus solid, and solidus phase. So number 1, phase 1 is solid. Number 2, that is between this 1250 degree, say at this 1250 degree, if you take B, point B, the same figure will be continued in the next problems also. So in this phase, liquid plus solid, and the third phase is liquid phase. So this is the rule 1, wherein we can say that how many phases are present. Say 3 phases: liquid, solid, liquid plus solid. Then next, if again we know temperature and composition, or that is percentage composition, we can determine the composition of each phase. Now since we have seen this tie line, this black tie line is there. Now example, what phase, when we say composition of each phase, so in that case, now let us take the example at 1320 degree. Let the temperature be 1320 degrees centigrade. So this is point A. Only liquid phase is present. Now when we say liquid phase is present, so by percentage weight Ni would be 35. Now in this case, this CO will be obviously equals to Cl, liquid phase, because it is at liquid phase. At D, this CO will be at C alpha. CO will be at C alpha, that is C solid. So at D and A, it would be liquid and solid respectively. Now at point B, say at point B. Now when I say at point B, so this is the liquid plus solid phase. Liquid plus solid phase. Again the same thing. But in this case, now let us see. In this case, the thing is CO. The thing is CO will be equals to C alpha again. The next one. That is D. D over here, the same ratio will be there. As we can, it is very much clear from the diagram itself, because at D it is solid. At D it is solid. Now here at B, I am repeating this fact. This tie line divides this into liquidus and solidus. So this is in both the cases. The third rule is, again, if you know temperature and composition, then you will be asked to calculate the weight fraction of each phase. Please mind well. Weight fraction, mass in fraction, mass fraction of each component or phase, the same thing. Now consider CO. Now consider this CO at 35% by weight of Ni. Then at Ta, only liquid is present. So Wl will be 1. W alpha will be 0. At this D, Wd will be 1 and Wl will be 0. Now the problem is, at point B, because B lies at liquid and solid phase. That's why, that's the mixed phase. At this point, we have to draw this tie line. Again, this tie line, where this tie line cuts liquidus line, will give us Cl, and where this tie line cuts solidus line gives us C alpha. Now, as we all know, say from the diagram itself, C alpha is having a value approximately equals to, it is represented given as 43, and here it is calculated as 32. So how to calculate then? We are calculating this for WL. Please mind well, WL. So in this case, we'll have to take C alpha minus CO upon C alpha minus CL. If it is W alpha, then how it would change? CO, as I have already given to you here only. Please concentrate. Yes. Here the liquid phase will come. We'll start with this. So again, the same thing. And this is how we can calculate W alpha on the same lines. So this is just, I have tried to explain all the three compositions, because it will be always asked in the examination about these three things. So we have taken this in terms of some rule 1, 2, and 3 for the sake of understanding. Now let us take and concentrate on this example. It is asked in the examination already. For a 35% weight Ni and 65% weight CuLi at 1250 degrees centigrade, it is given in the diagram itself. It is asked what phases are present. Number 2, what are the compositions of the phases. Number 3, calculate the relative amount of each phase present in terms of mass fraction. Now the things are very clear, as the tie line is already been drawn and the percentages are given. Okay, so directly we can assume also from the diagram itself, the composition itself is given. So this is at some 35, this is 40, so it will be between 40 to 50, so somewhere 43 we can assume. If it is generally it is given. If it is not, we can directly calculate it from the graph itself. Now see, the very first question is, how many phases are there? How many phases or different phases are there? So at this point, that is at 1250, when it is 1250, the phase diagram which is located within the alpha plus liquid region, say this is alpha plus, means solid plus liquid phase. Therefore both alpha and solid phases will coexist. So in this region, at this 1250, both the phases will be present. Next, what was our second question? What are the composition? So percentage composition we want to know. Since two phases are present, it becomes necessary to construct a tie line. So we have drawn a horizontal line, wherein this tie line cuts the liquidus line at, say, some point A, and solidus line, say, at some point C. So in that case, how we can write this as, say, about 43% weight of nickel here. So 57% copper. Similarly, at this point, if I want to say, so approximately, it is 30%. So 70% by weight of nickel would be there. Say copper will be there. So these are nothing but the second answer. All the way it will be asked in this fashion only. Always it will be asked in this fashion. So these are the things. The third one is, we want to know the mass composition. Calculate the relative amount of each phase present in terms of mass fraction. So that mass fraction we already know. That is if it is for solid, CO minus CL upon C alpha minus CL. If it is for liquid, then solid will come C alpha minus CO upon minus CL. So this would be the percentages. So this is how the binary system completely soluble in both the phases. So Cu and I, we have taken this example, and I hope you are getting the points. The next, now this is a eutectic diagram. This we have studied in our metallurgy, our material science, but why it is say present on this screen, the reason is just to revive the basic fundamental of eutectic diagram, because this point or this diagram is drawn when metals are completely soluble in liquid state and entirely insoluble in solid state. So here lies the problem then. So in this case, two separate region will be developed or generated on the graph depending upon the percentage or composition, and these two solid phases will be now represented by alpha and beta. Please mind well, this is represented by alpha and beta. Alpha for say A element and beta for B element. Because these two solid state or phase will always be there as the metals are insoluble in solid state. Now, here lies the point E, known as eutectic point. The temperature is known as eutectic temperature. The composition is known as eutectic composition. Now, first we'll have to understand this particular phase diagram for eutectic, and I hope and expect you got eutectic point. So this E is a eutectic point. The transformation will be from liquid to liquid plus alpha for element A, liquid plus beta for element B, and below this eutectic line, the element would be all solids. So here the transformation is from liquid to two solids, S1 and S2. So this would be the case, and that's why I have specifically explained the eutectic diagram. The next one, I think, yeah, example number 2. Now we are taking the example of PB and SN. So this is the percentage by weight of SN on the composition on the x-axis and temperature on the y-axis. Now the question is remains same. That is, this diagram or this phase diagram is given. This is obviously eutectic phase diagram. Now we have been asked at 150 degree, again the same thing. Now this phase diagram is shown with reference to the temperature 100, 150, 200, okay, and then 300, likewise temperatures. Now where lies Mr. 150 degree? So 150 degree will lie at this particular range. So 40% of SN. So we have drawn this temperature line 150, and we have cut this point. Now this, for us, this point is a CO. Now from this we will draw again the tie line. Yes, we have to draw the tie line. Now this tie line will cut solidus line at alpha, because this region is L plus alpha. Again, this region is L plus beta. So it will cut the line. So from the figure itself, it is clear that it is 11%. On the beta side, it is at some 99%. So this is nothing but this region is nothing but alpha plus beta composite section. So again, the same thing, how many phases will be present? How many phases will be present? Obviously, alpha plus beta. The next is the phase composition. C alpha is 11 and C beta is 99. The relative amount of each phase, again the same thing. That is for alpha, it is for beta element will be reference. So after beta, it is the alpha that will be reference. So we can calculate the relative amount of each phase in percentage composition or mass ratio from the diagram itself. So this is the second example wherein we can say, or we can answer all the questions 1, 2, 3 by simply observing and calculating the components. The next example 3, for 40% weight of SN and 60% weight of PB at 220 degree. Now please concentrate. When we say 220 degree, the graph at this point, again the 40%, but the graph, the point has crossed this eutectic line. So above this, when we said above this eutectic line, again the same thing. The phases present, obviously liquid plus alpha. The phase composition, now please draw this tie line. Now at this, say if this is 20, so somewhere here it is 17. And at this, if this is 40, this is 60, somewhere it is 46. So we have to write this. Again the same thing. This you can very well understand and solve by simply observing the second numerical itself. Now this I have given for practice session only. You can write W alpha or WL also, or ML, no problem. So this is simple for your practice handwritten notes with the answer, wherein we can solve this and we can get the answer. Because at different temperatures, different temperature will get different elements. So eutectic temperature, that is 183, it is mentioned here, so you can very well get. Now this is the question wherein we have been given the densities of PB and SN also. So this question, although it is not generally asked, but we have dealt with it. So depending upon this diagram, we can very well calculate W alpha or M alpha, W beta or M beta. So that is after calculation you can get it. I have directly given the answers. But since densities are given, so calculate the mass and volume fraction of the phase present in an alloy of PbSN with 35% SN at 100 degree. So this is the 100 degree line. Now when I say 100 degree line, it will cut alpha and beta curve, that is solidus curve at this point, and the percentage composition will be very well got from the diagram itself or the phase diagram itself. So you will be using densities and these formulas for this. Percentage 40% and 60%. So we'll get the density by using the same formula. So this is the new formula which we'll have to take into consideration, and we'll calculate the volume. This is for the volume, percentage of volume of this. Since V alpha we know, so V beta can be 1 minus directly alpha, that is 0.74. So this is again a very important, say, calculation part. Now, looking into the paucity of time and the amount of content, so we can directly now switch over to the iron carbon or FeC phase diagram that is very much popular by its name itself. So I just wanted to clear some of the points here, because these particular phase diagrams are the core or the say backbone of any steel and its alloy elements to select, to manufacture, for the heat treatment, for the composition content, for the percentage of mixing, and every good element related to steel and its alloys. This diagram must be referred. Now, one thing we must be very much clear about, I have taken the references which may not suit with reference to their temperature. Rest everything is common, but the temperature may differ between researchers to researchers or authors to authors. So in that case, since I am referring a particular author, this I have mentioned all the way in every say composition. So I am using the same author in all the cases. So in iron carbon diagram again, now see the different regions. You just see the different region, wherein this point A is known as a eutectic point, as we have already seen. But there is another point for this particular phase diagram, and that is known as point B, that is eutectoid point, wherein flakes are developed below this eutectoid point. Yes, you see the diagram itself. The flake-like structure will be there. And this is nothing but the percentage of carbon in the mixture of this iron carbon. And it will determine the different phases. See, the delta phase, the gamma, that is austenite, gamma plus liquidus phase, liquid plus dispersive phase. So these phases will be in depth. Say generally Fe3C is represented by the cementite phase. So this is eutectide and this is cementite. Again, I am explaining all these 5 phases basically in detail, because there are reactions also. For invariant reactions are there. So alpha ferrite, body centered cubic, solid solution. Gamma austenite, yes, face centered cubic, solid solution. Next, del ferrite, body centered cubic, solid solution. So again we'll refer, yeah, see, these are all solid solutions. There are solid solutions, solid phases. Fe3C, iron carbide or cementite. On the right side I have already represented. So an intermetallic compound and a liquid FeC solution. Yes, liquid FeC solution. So this is the region. So these 5 phases will be there. The 4 invariant reactions, that is peritectic, monotectic, eutectic and eutectide. At eutectide, so generally it is below 750 degrees centigrade and at 0.8% of carbon, that is at 723. Eutectic at 1147, monoeutectic at 1495. If you can see, the percentage of carbon is changing in all the way. Peritectic, see on the left, you can see at 1495, but percentage of carbon is 0.16. Yes, peritectic, see the region. So here it is. Now this is the complete diagram, wherein again I have tried to put more emphasis on the diagram itself. And now this diagram represents the basic percentages at each point. So we'll start with the ferrite. Where is that ferrite? Say this region at 1536, say above 1400 to 1536, this region is ferrite region. Austenite. So this portion below this ferrite, this is the austenitic region. This is the austenitic region. This region is again very important. Yes, generally the numerical is asked on this alpha plus gamma. Alpha plus gamma, this region. So ferrite. So this region is alpha is ferrite. What is gamma? Austenite. So this region, alpha plus this phase region, is of very importance. 0.02% carbon to 0.8% carbon in iron. So this is again, this is alpha, the solidus phase, the alpha. The next is this is nothing but eutectoid point, generally B. This is eutectic point, generally A, we used to call, and these are the different phases. Now, if you concentrate on this region is called ladyburite. Yes, this is ladyburite. If you concentrate on this region, this is pearlite, the hardest region, pearlite, pearlitic. So these are the different phases, and these are the regions on the iron carbon diagram. Now, this I have written so for your reference only, wherein we can say that the alpha ferrite or the ferrite austenite and del ferrite. So these three regions helps us to understand the composition as well as the melting point at or the temperature at which these occurs. Whereas cementite or FEC liquid solution, these are say very much essential part, again the phases, but this liquid solution is above 1538. So melting of iron generally decreases with increasing carbon content. So this is for simply the understanding. Now the problems, because these are very important elements. Now, as I have right now told you, we have to concentrate on this 0.8 to 0.02% carbon range, because generally the problem is asked over this region. The 725 degree, just now we have seen what this is mean for us. This is austenitic region. Yes. Where is that austenitic region? This austenitic region, this region. This is alpha plus delta. This is alpha plus gamma, but this austenitic region. So at this region, we have to calculate. Please mind well, this is 1% of carbon, so this is 0.8 and this is 0.02. So why I have referred always, because you can get this now. So this is alpha plus gamma, and this is austenitic region. So for this, when I say 725 degree or 723 degree centigrade, as I have told you, different books will have different temperature line, so it will be drawn accordingly, because you will be given one diagram itself, and you will have to understand this fact also. So now we'll draw the basic inference from this element. Now calculate the percentage of pro-eutectoid. See this is eutectoid. See, this is eutectoid region, because eutectic region is somewhere here, point A, and this is say point B. So in this case, how to get this? A very simple approach is there. So we have drawn this line over this. Now since point A, austenitic region, point B, alpha plus gamma, that is austenitic plus ferrite region. Point D, again this is the solidus region. So what do we expect? Pro alpha. Obviously solid region is there. Alpha is there. So in that case 0.8. What is this 0.8? Say this is CO. This is CO. So C alpha minus C, say C alpha minus CO upon C alpha minus, yes, this percentage of carbon which is associated with alpha. So this is the basic structure, wherein again it is expecting for total ferrite. So total ferrite, the reference would be now not 0.8, the reference would be 6.67. The reference would be 6.67. Yes, this 6.67. So this would be the region. This would be the region from here to here. So this would be the reference point. So we can very well calculate this or such type of problem. The next is again the same thing, perlite, say 0.8, again this is 0.02. On the same context, in perlite, what is the percentage of Fe3N? So this is the percentage, wherein we can say that from the diagram itself, 88% and 12%. The mass fraction can be very well calculated, but it was asked for the percentage of Fe3C, so we can get this. We can get this. So this is how the numericals will be dealt with. This is again very simple, and I have tried to cover maximum portion from it. Now the next part is heat treatment. Now the heat treatment is the backbone of retaining or maintaining the desired properties of material. Now what are the objectives of heat treatment? To improve mechanical property, to improve machinability, to refine the grains, to relieve these stresses or residual stresses from the machined parts, to overcome effect of strain hardening and restore ductile property. So heat treatment is generally seen as the process of getting the desirable properties imparted on the workpiece, on the materials. So heat treatment will be done by taking the phase diagram as the reference, after which we can get the proper heat treatment processes. So phase diagram must be referred in any case. Now classification of heat treatment, generally heat treatment are as it is generally given in the books. Full heat treatment, it means full body heat treatment, and number 2, surface heat treatment. When I say full heat treatment, it means annealing, normalizing, hardening, tempering, and etching. When I say surface heat treatment, it means that the surfaces are the targeted section for this type of heat treatment. That is carburizing, cyaniding, nitriding, quenching, etc. So these are the. So annealing is the process of basically softening the material or to bring about the required changes in properties. So how annealing is done? Heating the steel near the critical temperature or the crystalline phase change occur to make it suitable for fabrication. So this is the annealing range. This you can see the belt. So at this ferrite plus perlite, this is cementite plus perlite. So the percentage of carbon range may be changing, but the temperature range is very important. So annealing process range is this in between. So generally it is 659 degrees centigrade to 712 degrees centigrade. The range is generally defined. So annealed part are nothing but the acquisition of softness in the material. Next is on normalizing. See, it is another part or the next type wherein the material is allowed to cool, because in annealing the material is allowed to cool at a slower rate, whereas in normalizing this is generally applicable to ferrous material. In annealing we use higher temperature and then remove from the fire, say air cooling is done. Normalizing is used in plates, large forgings, railroads, axles. So these are used. And now see, this is the normalizing range. Normalizing range is represented by this graph on the temperature composition, that is the graph itself. Okay, so next. So this is the different phases represented by the TTT diagram, that is time temperature transformation TTT diagram for annealing and normalizing. So from coarse grade to fine, the paralytic region which is obtained by annealing and normalizing, the bainite region will be obtained. So this is the annealing portion and the normalizing portion. The next is hardening. Now the word hardening itself is basically the treatment wherein the process involved rapid cooling from austenitic temperature, and as a result the hardness and wear resistance of the steels are improved. So this is hardening. Now generally ferrite and perlite transformation to austenitic at high hardening temperature for hypoeutectite steel, which is generally required. See, this is the case. See, this is the case. See, this is the case. So this is normalizing. This is full annealing portion wherein hardening is done at this region. So the next is aging. Now aging has a very basic what we can say the logic that you have to hold for a long time. Holding that particular material at the temperature for a long time and then release it, the aging will be done. The aging will be done, and due to that aging or the hardening behavior, so the hardness will increase. And obviously after some period of time the hardness will go on decreasing. So this is aging. In this, the next one is carburizing. This is very famous process for our gears, clutch plates. I insist, gears and clutch plates, we use carburizing. It is carried out on steel containing carbon less than 0.2%. It involves increasing the carbon content on the surface layer up to 0.7 to 0.8%, from 0.2 to 0.8%. In this process, the steel is heated in contact with the carbonaceous material from which it absorbs carbon. This method is mostly used for securing hard and wear resistant surface with tough core for gear, cam, bearings and clutch plate. So a surrounding is provided. Carbonaceous material, say twice CO is equal to CO plus CO2. So these are the generally or frequently used methods of say carburizing, wherein solid carburizing is there, gas carburizing is there, and then we say liquid carburizing is there. So this is how solid carburizing, gas carburizing and liquid carburizing, they have depicted it with the diagram itself. Nitriding, heating the component in, say, allowing ammonia gas. Basically in nitriding, the ammonia gas is allowed to circulate and the temperature of ammonia dissociate the surface. Yes, wherein the nitrogen, atomic nitrogen diffuses into steel surface and combines with the alloying element to form hard nitrides. Again, the surface phenomena. Now nitriding increases wear and corrosion resistance and fatigue strength of the steel. Fatigue strength of the steel. The next is cyaniding. Again, the surface heat treatment, and generally this cyaniding is used for durable parts such as small gears, nuts and bolts, screws where shock absorption is generally done, and as well as the area or the range of applicability is very large. The component is generally, after allowing the component in bath for about 15 to 20 minutes, they are quenched in oil or water. Cyaniding is normally used for low carbon steel and case depths are usually 0.25 mm. So this is cyaniding. Now the last portion, stress strain diagram. Basically stress strain diagram is the graphical representation of the relationship between the applied load and the elongation produced in the metallic bar. A specimen is taken and it is tested on universal testing machine, whereas the extension or the elongation can be measured using either dial gauges, and now it is extensometers. So extensometers can be used to measure the stress strain. Here we can say that the stress strain curve provides the properties of material with reference to different points on the graph. These points are drawn for a specimen tested on UTM under tension or tensile load. So Young's modulus can be very well calculated and different properties can be studied from this. Now just consider, this is for the sake of understanding, I have represented with this graph at the regions, so that the aim of this particular lecture would be met according to me. The graph itself shows the elastic behavior. When some load is applied, when load is applied, as load increases, stress will increase obviously, so the deformation will also increase. If we again increase, then the next point will come. The point up to which the bar or the material regains its elasticity. If I leave this load from this rod or the specimen, it will deform and it will acquire its original position. We say that it is having elasticity. So this region is known as elastic region. And after this elastic point or elastic limit, if I again increase the load, the stage will transfer into plastic stage, where permanent deformation would be there and yielding will occur. So this is the yielding. Now after that, if we again go on increasing the load, obviously deformation will decrease, but now the deformation will increase abruptly. Now this abrupt change will be known as strain hardening, and there would be a point known as ultimate stress point, wherein at this ultimate stress point we can say that at this point the material has acquired its maximum capacity to withstand the applied load before its actual failure or fracture, and after this it may fracture. So after ultimate, if we again slightly increase, the fracture will occur. So at this portion the necking will be done and it may break at any point. So this is the stress strain diagram for ductile material. Now, so this is for brittle material. Since the property of brittleness does not allow the material to deform progressively. So at some point it may deform, but at the very next its deformation will be restricted due to the property of its brittleness, and it will suddenly fracture, known as stress strain diagram for brittle material. Now I have represented stress strain diagram for cemented tungsten carbide. A simple stress strain diagram, because when I say tungsten carbide, so the graph is linearly varying. So that is the essence of that particular material, wherein whatever may be the load applied, the strain or the deformation would be proportionate. So, and the next is for rubber. Now see the beauty of this particular graph. Since I've considered the soft rubber, now see the graph itself tells us the characteristics of rubber, how it is, say under tensile load, how it is behaving. So this is all about today's lecture, and I hope that we have covered to the maximum extent and the numericals which were required and generally asked in the examination. Thank you so much, all of you. Thank you so much.